Hi everyone, welcome to Orgo Essentials, not your basic organic chemistry tutorial, Episode 8. In this episode, we'll learn about electronegativity and polarity, discuss some organic compounds containing dipoles, and discover the relationship between a molecule's geometry and its dipole moment. Let's get started! Over the past few videos, we've been discussing molecular geometries, which heavily depends on the location of electrons. We've learned that bonds between atoms are composed of bonding groups of electrons, shared between the two atoms. However, sometimes these bonding groups are unequally shared. This occurs when the difference between two atoms' electronegativities is great. Electronegativity refers to the ability of an atom to attract electrons to itself in a bond. As you might expect, some elements, such as fluorine, are very electronegative, which means that electrons are much more likely to be closer to the fluorine atom than to the other atom in the bond. On the other hand, some elements, such as hydrogen, are not very electronegative and are more likely to give up their electrons. In general, electronegativity can be predicted by following the trends in atomic radius of the periodic table. Smaller elements, found in the upper right-hand corner of the periodic table, tend to be more electronegative. This is because, in these atoms, the nucleus and its positive charge are closer to the electrons and their negative charge, resulting in a stronger attraction between the two. This means that more energy will be required to take the electrons. As we move down and to the left, atomic radius increases, and electronegativity decreases. This is because, as the outermost electrons move farther away from the positive nucleus, the electrostatic attraction between them decreases, resulting in less energy being required to take the electrons. While understanding these periodic trends is important, there is a more specific way to measure electronegativity. American chemist Linus Pauling created the Electronegativity Scale, in which every element is assigned a number corresponding with its electronegativity. These numbers range from 0.7 for cesium and francium in the lower left corner of the periodic table to 4.0 for fluorine. Don't worry, you don't need to memorize these numbers. They can easily be found in textbooks and online. If you don't have access to these resources, simply rely on the more general periodic trends. The electronegativity scale allows us to classify covalent bonds into two groups, polar and nonpolar. Recall that covalent bonds are most often between two non-metallic elements. Most bonds in organic chemistry are covalent. In covalent bonds, electrons are shared between two atoms. However, as we hinted at in the beginning of this video, sometimes electrons are shared unequally. These types of bonds are called polar bonds. They occur when there is a difference in electronegativity, sometimes represented as DEN or delta En, between 0.4 and about 1.7 or 1.8. For example, an OH bond is polar, since the electronegativity difference is 1.4. Since the oxygen atom is much more electronegative, it will attract the electrons closer to its nucleus than to the hydrogen atom's nucleus. In nonpolar bonds, the opposite occurs. Electrons are shared fairly equally. This happens when the bond is between two atoms of the same element, such as HH, because the DEN will be 0. However, this also happens when the bond is between different atoms that have similar electronegativities, like in a BH or OS bond. One of the most common bonds in organic chemistry, CH bonds, is also nonpolar. The difference in electronegativity is only 0.35. These nonpolar bonds, though common, are kind of boring. Let's get back to the polar bonds, like the ones in this water molecule. Remember that oxygen is the more electronegative atom, so it will attract the electrons closer to itself than hydrogen. This forms a slight negative charge near the oxygen atom, since electrons are negatively charged, and a slight positive charge at the hydrogen atoms, since their valence electrons are being taken away. These are not full charges. That would be an ionic bond, with electrons being fully transferred from one atom to another. They are partial charges, represented by lowercase delta, like this. These partial charges together are referred to as a dipole. A dipole is drawn on the molecule as a crossed arrow, with the crossed end at the less electronegative atom and the arrowhead at the more electronegative atom. Dipoles are vectors, meaning they have magnitude and direction. Every molecule with dipole bonds doesn't necessarily have a dipole moment, which is basically the molecule's overall dipole, with magnitude and direction. This is because certain molecular geometries are symmetrical, so the vectors cancel out. Here is a list of symmetrical molecular geometries in organic chemistry. If a molecule has one of these geometries, and its dipoles all have the same magnitude, meaning the bonds involved all have equal DENs, then there will be no dipole moment. For example, let's look at carbon dioxide, CO2. We can see that the Lewis structure has a linear shape, which is symmetrical. Since the DEN is greater than 0.4, we can draw in the dipole bonds, with the pluses near the carbon atom and the arrowheads near the oxygen atoms, like this. This molecule has dipoles, but they end up canceling each other out. We can prove this by adding the vectors, using the head-to-tail method. When we add the vectors, we get zero displacement, with the second arrowhead landing on the first arrow's plus. There is no dipole moment. Sometimes, though a molecule has a symmetrical molecular geometry, its individual dipole bonds have different magnitudes, resulting in a dipole moment. For example, here is the Lewis structure for hydrogen cyanide, HCN. As we know, this molecule is linear, which is symmetrical. However, we only have one dipole bond, a small one between the carbon and the nitrogen atom, drawn like this. There is no dipole bond between the hydrogen and carbon to cancel this out, so the molecule will have a dipole moment. That's it for this video, and actually, that's it for our whole introduction unit. I've included a study guide to all the topics covered in this unit, from Lewis structures to hybridization. If you have any questions so far, feel free to email me or comment down below. Remember, practice only makes better. The next video will be the beginning of our new unit on nomenclature and alkanes. In it, we'll learn about the common organic chemistry functional groups. I'll see you then!